In this video we're going to look at the subtractor, or it's called the difference amplifier. So this is our little circuit here, and we can see that what this circuit does is it takes the difference between these two voltages and amplifies it and by a certain ratio, and gives it as an output voltage here. Okay, so let's have a wee look and see exactly how it does that. So what we're going to do is we'll analyse it the same way we analysed the previous circuits. We'll look at the voltage at the V minus side, and then we'll look at the voltage at the V plus side, then we'll make the V plus equal the V minus. Okay, so that's what we'll do here. So we'll start off here looking at the currents in this leg here. So we can see then that VA minus V plus upon R3 is a current in that leg there. And we know there's no current flows into the input of the op amp, so all that current must flow down through there. So that current must equal that current, which is going to equal V plus minus 0 upon R4, which is just what we've got here. So what we'll do is we'll take this V plus across, and then we'll gather the like terms. So we'll take out the common factor here, V plus, and it will leave us with our minus 1 upon R3, minus 1 upon R4, and we'll take the other term here across to the other side. It's minus VA upon R3. Now we've got to rearrange that to get V plus, so it's just a bit of algebra. So V plus is going to equal VA upon R3, and the minuses all cancel out there, and it's going to be we take this whole term down to the bottom, and then we'll take the common factor of R3 times R4, and that will give us R4 plus R3 in that line, and we're dividing throughout by this value. It's the same as we're multiplying by the reciprocal, and then we can cancel out, and when we cancel out it gives us our V plus equals VA R4 upon R3 plus R4. Okay, so that's the first part of our little derivation. So we've got the voltage here at V plus. Now we're interested in the voltage at the other leg here, so we're interested in the voltage at V minus. So in this other leg here we'll have VB minus V minus is this current here, all upon R1 is that current, and the current in this leg here will be V out minus V minus upon R2 would be this current here. Okay, so I've got that noted down here. So that's these two, and those summation of those two is going to equal 0. So we open this out again, so we get a V upon R1 minus V minus upon R1 plus V out upon R2 minus V minus upon R2 equals 0. Okay, now we'll gather like terms again. Our V minus equal 1 upon R1 plus 1 upon R2 is going to equal minus VB upon R1 plus V out upon R2. Okay, so get this fixed there. So what we can do then is we want to find out what V minus is, so we can take this whole lot down. So first of all we'll take a common factor, R1 times R2, and that will become R1 plus R2. We take that down, it will be the reciprocal, so we get this here. Okay, so this is going to be our V minus. So talk through that quite quickly, but what you can do is, I suggest you do, is just work through the derivation yourself, and you'll see, and it's also a check and see I've got the derivation correct. So then we use our golden rules. We know there's no current flowing into, well, we know that the V plus is going to equal the V minus, so it means that this V plus here is going to equal the V minus here. Okay, so we just equate these two equations. Now I'm not going to talk through the derivation, so you can just work through the derivation there yourself. The only one thing to note is that in this instance here we add an extra proviso that we want the ratio of R4 upon R3 to equal R2 upon R1. Okay, so that's one extra that's added into this circuit here. So finally, if we were to look at the last couple of lines here, this is a value for our V naught here, and we can rewrite it there by taking out this common factor, and we're finally left with our V naught equals R2 upon R1 VA minus VB. Now that's only true if R2 upon R1 equals R3 upon R4, okay, in this particular design. So I suggest you take your time to read through and derive it yourself. I didn't want to read through every single part of it because it's just a little bit dull, and it's just kind of bulk algebra. Now, if we were to look at it in multisim, so that's the circuit for this subtractor or difference amplifier built up in multisim, and you can see that our inputs here are a 3 volt peak signal and a 2 volt peak signal, so it's going to amplify the difference. So the difference is going to be 1 volt peak. Now I've set it out with the resistor values so that the amplification is only a value of 1. Okay, so we should only get, it should take a 3 volt signal and take away the 2 volt signal and just give us a 1 volt signal at the output. So let's have a look and see. And there you see, that's exactly what multisim has done. We've got our 2 volts signal in here. Okay, so that there is our first input, and we've got our 3 volt signal in red, that's our other input, and the amplifier amplifies the difference. So the difference between these two is 1 volt, and it's going to amplify it by a factor of just 1, so you just get 1 volt on the output. Okay, so that there is the difference amplifier. I suggest you go and you can build it yourself, or I've got the multisim simulation there, and so you can just download that if you've got the tool, and you can go and simulate that there for yourself. So thank you for listening, and I'll go on to the next video will be the instrumentation amplifier, and that will really finish off this little look at just the simple way to analyse op-amp circuits. Okay, thank you for listening, and goodbye.